Okay, everybody, welcome back to part 4 of electrophilic aromatic substitution reactions. Now, okay, so we'll talk about what if you have, instead of just one electron donating group, or if you have one electron withdrawing group, what if you have more than one present on the starting material, the aromatic ring? What would happen? How would you direct the substitution or the addition of that new substituent onto the aromatic ring? Well, I have done a little bit of a layout for you of how to be able to determine that. So I'll go through some examples. So let's just say, if you have a strong electron donating group and a weak electron donating group present on the starting material, the strong electron donating group will direct the position of the incoming substituent. So for example, and for all the examples I'll be talking about halogenation. Okay, so if you have an aromatic ring, right? If you have an aromatic ring with a strong electron withdrawing group, strong electron donating group, sorry, right? It has lone pairs, remember, it's donated by resonance, so it's very strong. If you have a strong electron donating group now, and let's just say you have a weak electron donating, let's just say you have a 2-carbon alkyl chain hanging off of it, a ethyl group. Now the halogenation, like I said, I'll be talking about halogenation only. Where will the halogen add into this carbon? Which hydrogen would it substitute and add to? So since this is a strong electron donating group, again, it will direct to the ortho and pair position, and this will direct the positioning of the incoming bromine or chlorine. So this has no say in the direction or in the direction of the bromine. This has all the say, this OH group. So again, let's label it O M P. Again, this is O M P, right? Now, since this ortho position is already occupied by this ethyl group, the Br cannot add into this position. It cannot attach to this carbon. Okay, there are no H's, any more H's here to be eliminated to reform the double bond. So you can't do that. So this ortho position is vacant. So you could have one of your products with the bromine here, and the other product with the bromine here. So it'll look like this. So if this is your H, right, and this is your ethyl group, and this is your aromatic ring, you have one product with the Br here, right, and the other product you'll have will be the aromatic ring, right, you have the aromatic ring with the bromine here. Okay, again, pair position, ortho position. That position is already occupied, so you cannot have the bromine attached there. And so that's the first thing. Now the next one. Now what if you have a weak electron donating group and a weak electron withdrawing group? Now the weak electron donating group will determine the position of it will direct the position of the incoming substituent. And again, I'll be talking about halogenation. So let's just say, so if this is your aromatic ring, and let's just say you have, again, keep it constant, you have an ethyl group there and weak electron withdrawing groups. You guys need to know the weak electron withdrawing groups and donating groups and all that stuff. You need to know them by memory. So let's put a Cl here. This will determine the position of the incoming bromine. So let's label it O, O, M, M, and P. Okay, so you form two, actually in this case you'll form 3 products. Okay, now I'll explain why. I might have to do this on a separate piece of paper. you'll form. Okay, so the first product, you have a Cl there, right? You have a Br there. Okay, you have a Br there. Now the second product, see it's in the ortho position. Second product will be in this ortho position, because this ortho position is not the same as this ortho position. You see, this bromine was in between these two groups, between the chlorine and this ethyl group. Now the bromine is not in between those two groups, so it's a new different position. It's something different from this. You cannot rotate the molecule in any way to form this. You can't. You just can't possibly do that. So this is a separate new product. So you need to be aware of that. You need to know about, have a little bit of idea of three-dimensional, just about three-dimensional stuff, okay? And the third product you'll form will be, as you guys guessed, in the para position. Okay, so right there. So your Cl's there, and your ethyl group is right there. So there you have it. This is the second type of things you guys need to be aware of if you have a weak electron donating group versus a weak electron withdrawing group. And you guys can just imagine if you have three groups then attached in the starting material, like a strong electron withdrawing group, a weak electron donating group, and a strong electron donating group. So strong electron donating group and a weak and a strong. Okay, I apologize, I just confused myself a little bit by saying all those words all at once. So you guys get the pattern, and it applies to even 3 or 4 substituents. So if you have a strong electron donating group, you have a weak electron donating group, and say for example if you have a weak electron withdrawing group, the strong electron donating group will determine the direction of the incoming group. So you guys will get the pattern. So all it is a little bit of practice. Okay, the third one is weak electron withdrawing group and strong electron withdrawing group. The weak electron withdrawing group will direct the position of the incoming group, incoming substituent. So the weak electron withdrawing group that we'll be focusing on are halogens, but there's a little twist to that. Halogens do not direct the incoming group to the meta position like all typical electron withdrawing groups do. Halogens are similar to electron donating groups. Even though they're withdrawing groups, they direct the incoming group to the ortho and para position. So that's the only exception you guys need to be aware of. If that halogens, I'll even write it. So this X represents halogens, okay? It directs it to the ortho, O for ortho, and P for para positions. Alright, halogens on top. Halogens, okay? Be aware of that, okay? So, for example, if you have this aromatic ring with bromine, let's just say CF3, right? I don't think you guys can see the CF3. Now, the bromine will direct the incoming group, say because we're doing halogenation still, it'll direct the BR to the ortho and para position. So let's label it again, O, M, P, M, O, okay? It'll direct it to the ortho and para position. So your product you'll get is you'll have this bromine here, you have the CF3 there, right? You have a bromine here, plus you have a bromine here in the ortho position, and let's just say you have a CF3 3 there, and you have your bromine there. Okay, so this bromine directs it to the ortho and para position. So there you got the ortho position and the para position. Now the final thing we'll be discussing is if you have a strong electron withdrawing group and a moderate electron withdrawing group. The strong electron withdrawing group determines the positioning. So let's give an example. Let's be consistent. You have your aromatic ring, right? And let's just say you have CF3 right there, and you have, let's just say we have a ketone, okay, and we're doing halogenation. Remember, electron withdrawing groups, with the exception of halogens, directed the incoming group to the meta position. So let's label it O, O, M, P. There's another M right there, okay? So the Br will go to this meta position only, so you have only one product because this meta position is already occupied, okay? So your product, which will be only one product, will be, you have your CF3 there, you have your ketone there, and then in the meta position, which is right here, you have your bromine. And there you have it. Those are all the tools you guys need in order to do these types of problems, these electrophilic aromatic substitution reaction problems. And so if the professor or your teacher tries to throw any types of variations, like starts you off with some tricky starting material, you know exactly what to do by these sets of rules that I have showed you, and I'll just underline every single one of them so you guys will be set. And we'll do some example problems, I think, in the 5th part of this topic. So there you have it. A little recap: strong electron donating group versus weak electron donating group. Strong electron donating group directs ortho and para. So our O and P for ortho and para. Weak electron donating group versus weak electron withdrawing group. Weak electron donating group directs ortho and para. Weak electron withdrawing group versus strong electron withdrawing group. Weak electron withdrawing group directs. And since the weak electron withdrawing groups that we'll be focusing on are halogens, they will direct to the ortho and para position. So keep that in mind: halogens, ortho, and para position. Okay. Now, final one: strong electron withdrawing group versus moderate electron withdrawing group directs. The strong electron withdrawing group directs ortho and para. And just one more thing I want you guys to know is that, so even if you had a weak electron withdrawing group versus a moderate electron withdrawing group, the weak one will also direct the incoming group. So there you have it. And so in part 5, I believe, I think it will be part 5, we'll be discussing some examples and going over how to be able to do it. And maybe I'll do a part 6 on some synthesis reactions on how to make a certain product given certain starting material. And eventually another video topic I'll be discussing is the reactions on the substituents attached to the aromatic ring. Alright, so please stay tuned to part 5. Thank you.